Yeah, so we got a test coming up on Wednesday, last test, and then the final. Mm-hmm. Yeah, if you want it. I don't know. It's something I wrote a long time ago. Uh, yeah, a bunch of formulas. Did y'all look at the practice test? Any questions on the practice test? Looks like maybe there was an error on the answer for 11.2. Did you find that one? It says the answer is supposed to be 3.7 kilowatts, and I think it's supposed to be 7.4. Okay. And that was with the 1/2, so yeah, it's yeah, okay. Just one. Yeah, I mean, that's with the 1/2, so without the 1/2, it would have been even like 15 or 14.8. So I don't know what they were thinking on that one. So solutions for the chapter 11 problems are here, but the other ones are all for you to find. Have to do some Thevenin equivalence. So it's really a chance for y'all to get any questions answered. We could talk about quiz questions too, if there was any questions on those. Are the quizzes all done now? I think they're all done, right? Quiz 8's closed. No, quiz 7 says it's available for some reason. Question? Yeah, it's an extra credit quiz, although I can't make it show up as extra credit yet because it won't let me give it 0 points. But yeah, so you don't have to do it. It won't affect your grade if you don't do it. Yeah. So yeah, any of these questions, quiz 8, quiz 7. Sure why that one's still open. No, it's closed. So whatever you want to do, you want to just work the problems out on the board with a partner, practice test 4 problems, or any kind of questions of the quiz. It's really, I don't have anything to talk about, so yeah. Yeah, that was due May 13th. Yep. Yeah. Some of the ones that were multiple choice that had, for example, the problem was like, but the magnitudes were wrong. Like I was getting magnitude like 11 point something, and all the magnitudes were 6. And it didn't matter because they were all the same. So all that mattered was not just angle. Yeah. But I was wondering if anybody else thinks that. Well, let me pull up the review. See. If you can, can you remember what the that one?
So you got that this was not 16?
That's what I was getting. But
you were getting 16?
No.
You were getting 11 or something?
Yeah, I was going to negative 8 minus 8.
Huh. Everyone else do this problem? So these are great, right? Because they have dependent sources and I don't know what this thing, it's just 4, I don't know what that square is. 4, supposed to be a multiplication, 4 cosine of 2t. And you got C here, so, and you're trying to find the forced response is what? And you've got 4 angle 0 here. And this is going to have minus j over omega c, which is going to be omega 2c. So this is going to equal minus j over 2.25. It's going to be minus 4j, right? So minus 4j is z, and you can say, well, okay, so you've got 4 angle 0 going here, you got g vx going here, and so you can pretty much, well, and you can define this current as vx over minus 4j, right? Going that way. Does that make sense? So you can do KVL or KCL, which says 4 angle 0 plus 0.25 times Vx minus Vx over minus 4j equals 0. So does that look right so far? Any mistakes? Right? Oh, there's a root 2 there. Did you get a root 2? Maybe your browser knocked it off. Yeah, that square is supposed to be a root 2.
There you go.
Okay.
Not that square on YouTube.
There was another question like that, you're saying? Okay. So you inferred that the square was a root 2 symbol. Did anyone else have a square there? Okay. All right. Well, that's annoying. Do you remember there being a root 2? Well, you might not have gotten it. It's a random selection of problems. So, okay. So, dang. All right. So it's supposed to be 4 root 2. And, but then, that being okay, we still have 0.25 Vx, and we have minus Vx over minus 4j equals 0. So this should give us Vx times, well, that's going to be plus, so that's going to be Vx times 0.5, right? And that's going to equal, well, this becomes, oh, sorry, there's a J in there. Never mind. That would have been nice. Vx times 1/4 plus 1 over 4j equals minus 4 root 2 angle 0. And we could also write this as minus j over 4 with the j on top, right? Everyone cool with that? And this is basically 1/4. No, it's 1/4 root 2 angle minus 45. I'm just guessing. Is that right? That's 1/4. If it's 1/4, 1/4, you're going to have 1/4 root 2 as the magnitude. It's going to have an angle of minus 45 degrees, right? So polar form can make that kind of easy. So Vx times that equals minus 4 root 2 angle 0. So that means we have to solve for Vx, and that's going to equal minus 4 root 2 over 1/4 root 2, and that's why we have 16 there. The root 2's cancel, and then the 45 comes up on top, and this becomes 16. 16 angle 45, negative 16 angle 45. And negative 16 angle 45 means, and you can kind of do this in the complex plane, you go negative 45 degrees, but then you got to go negative 16. So that puts you up here, which gives you an angle of 135 degrees. Oh, it's positive 45. Thank you. Positive 45. And then negative 16 is going to be negative 135 degrees. Ollie? Because this square here was supposed to say square root of 2, but it said square. So, yeah, when you see square, that means square root of 2. Right, doesn't that kind of make sense that this should sort of mean the square root of 2, because the diagonal is sort of the root 2 of the edge? Yeah. No, it's a mistake. It should have, it's somehow the browser or something got screwed up. Let's see if it actually says it. Yeah, it says square root 2 there. Now, this is the kind of thing I have to do to fix these errors, which is really annoying. I have to go in and, what question was this? This was for, you don't care about this, but I do. Question number, what question was it, 11? Question 11. So I got to go here and this is why I groan every time somebody finds an error. And then I go edit quiz banks. And unfortunately, so I think it's 1, 2. So that should be this one. That one. Well, that's weird. That doesn't even have a root 2 there at all.
Yeah.
But how did that turn into a square? Very strange. So I can put a square root of 2 there. because there are these symbols here. So let's see, I think I can do. But sometimes, you know, certain browsers will also mess these things up. So. Now the problem is just updating it here doesn't actually fix the problem in the quiz. So I have to actually rebuild the quiz, but I'm not sure I can do that right now, but when I. Yeah.
So on this one, which node did you use KCL, right?
Mm-hmm. I did it at the top node.
That the one.
Yeah. Mm-hmm.
And you found the VX.
Yeah, we saw it for VX. Yep. Yeah, these are great practice problems. They're really elemental. They got fundamental, elemental. Yeah, they're just doing the basics, but they, you know, if you can do these, then you can tackle the larger ones, bigger ones. Oops, for quiz 8.
Yeah.
Oh, Yeah, it's interesting that it was. Oops, I don't want to edit it. It was interesting that it showed up in the review question, but I guess you noticed that people noticed that same square in the real one. Because I have to remake both the review quiz and the actual quiz. Okay, any other ones we want to look at? That one? We just did that one.
Can you do that crazy one? The hot count, the crazy one?
Which one?
This is this one.
That one? It's not crazy. It's only crazy if you've never seen op amps before. Because having seen op amps before, you'll know that these are what kind of op amps. Cascading isn't really what kind of op amp is the first op amp? What kind of amplifier is the first amplifier? What? It's a non-inverting op amp. And what's the second one? What kind of op amp is that? It's the same. It's a non-inverting op amp. So you have two non-inverting amps. What's the gain of a non-inverting op amp? You don't know? You're supposed to. Those are really, you should have those handy, you know. Whenever you have an op amp problem, you should have those handy. That's why this is not crazy. It's really easy if you know the gain for an op amp, a gain for a non-inverting op amp is. Anybody? R over JX? No. Yeah, minus VP equals 0. You can solve it, yeah, but anyone remember what it is? Well, you could approach it the classical way if you want to, but it takes longer, right? So, and doing it with complex numbers is not the most pleasant way of doing it, right? But if you put them both back at resistors or something, then you know it's a little bit easier. So you could go on the side here and just say, okay, I got a VS here, I have a plus, a minus, and I have an R1 and an RF and a VO, right? And basically this point right here, we could call this V1. V1 has to equal Vs, right? Because the op-amp constraint. And but there's no current coming out of there. And so actually V1, which is the voltage across which resistor, that node voltage V1 is really the voltage across which resistor? R1. And what formula can we use to find V1 relative to V0? Nope. Sorry? Far voltage minus near voltage of a resistor, but there's an even quicker formula. Voltage divider formula, that's what I'm looking for. Again, you know, it's the suspect that no one ever suspects. So you should always suspect it's a voltage divider. How do you know that? How do you know that? Well, what's VO? VO is the voltage from this node to ground, right? And since there's no current coming out of the op-amp minus terminal, right, then that's sort of like an open circuit, meaning you could sort of essentially erase the op-amp. And then what do you have? A voltage divider. Yeah. It's pattern recognition. Yeah, I see. Well, you can't really ignore it, but when you're trying to figure out what V1 is, you can ignore it because the op-amp is changing VO so that V1 is going to be the same as VS, right? But it can't change KCL and KVL, and that tells you that the relationship between VO and V1 is going to be R1 over R1 plus RF times VO. You could prove that with nodal analysis if you want. You can use Ohm's law. You know, VO minus V1 over RF has to equal V1 over R1, right? You could do that, right? Right? Isn't that what you were saying, David? This current has to equal this current, right? So VO minus V1 over RF has to equal V1 over R1. And then you can solve for VO as well. So VO is going to equal, so VO over RF is going to equal V1 over R1 minus or plus V1 over RF. So then you multiply both sides by RF, and you're going to get VO equals, well, let's factor out V1 times R1 plus RF, but then that's going to be multiplied times RF. But actually, we want to solve for V1, right? So let's keep the RF over there and keep going. So V1 is going to equal VO times 1 over R1 plus 1 over RF over RF. Is that the same as R1 over R1 plus RF? Well, if you multiply, did I mess something up? Well, I was just thinking KCL, right? VO minus V1 over RF is this current. And V1 minus 0 over R1 is that current. So those should be the same. So VO over RF, should we multiply everything by RF? What's that? Oh, it should be on the bottom, right? It's VO over RF divided by 1 over R1 plus 1 over RF. Thank you, Vaughn. This is why I use those formulas, right? Because then you don't make as many mistakes. R1 plus 1 over RF. And then you get the RFs over there canceling. And so you end up getting equals VO times RF over R1 plus RF. RF over, no, that doesn't work. It's RF over R1. This is why I have to have a I have to have a script. So it's VO. Now let's see, we probably could get a common denominator here, right? We could get common denominator R1, RF, and RF, R1, if we multiply this by RF over RF and this by R1 over R1. So then we're going to get, and then the RFs will cancel, right? And so then we're going to get VO over RF plus R1 over R1, which equals VO R1 over RF plus R1. So that's the voltage divider formula.
So the total gain would be 2 times that.
Well, you would square it. The total gain for both cascaded amplifiers, you mean? Mm-hmm. Yeah, you would basically want to square that because you've got basically the same thing, and you're cascading it. By cascading, you're actually multiplying. You're doing that gain thing twice. Let me erase all this stuff. So this is how I do this. I look at that thing and I say, oh, that's an inverting amplifier. And you have to do this all over again. So right, you can do all that stuff, but it's really painful. And well, we didn't even prove what that gain was yet. We just proved what we just proved that V1, which has to equal Vs, also has to equal R1 over R1 plus RF times VO. And but that tells you that the gain, which equals VO over Vs, is going to equal taking VO over Vs, you're going to have R1 plus RF over R1, right? Which equals 1 plus RF over R1. That's the gain of a non-inverting amplifier. And if you just had that on your formula sheet and you could recognize that that's a non-inverting amplifier configuration, then you can just plug that formula in there and just say, well, if you got 2 of these things in a row, right? So if you call this maybe V2 is going to equal 1 plus, and let's call it ZF over Z1 over Z1 times Vs, right? That's what V2 is. Well, VO has to be another gain times, right? So VO has to be 1 plus ZF over Z1 times V2, which equals 1 plus ZF over Z1 times 1 plus ZF over, you're squaring your gain, right? Vs. ZF is the feedback impedance, which is what you're going from the output to the minus side, and Z1 so this is Z1 and this is ZF. That's the pattern for an inverting op amp. We just call that Z1 or R1. And so yeah, you can plug that in. So if in this case R equals Z1 equals in our case 5 ohms, and X is, well, JX is ZF. That equals minus 15. So ZF equals minus 15J, right? You then have to plug that into these formulas and do the math. So our VO is going to equal 1 plus, it's going to be minus 15J. Nice thing is these numbers tend to work out fairly nicely. And 1 minus 15J over 5 times Vs. Well, Vs is basically just 2. Oh, is that what you said, multiply by 2? You said multiply by 2 earlier?
Oh, no.
2 times that? No, yeah, it's a square. Yeah, but that signal also has to be included as well. So our total VO is going to be 1 minus 3j squared, right? Times 2. So that becomes 1 minus 6j. And then this is going to be plus 9, right? Times 2. Is it negative 9? Well, it's going to be, yeah, it's going to be 9j squared, right? It's going to be minus 9. So that's going to equal 8 minus 6j times 2. So that's going to equal 16 minus 12j. So it should be this answer right here. Oops. Oops, it's minus 8 minus 6j, right? Yeah, it should be negative 16. Sorry, I made another error. Minus 8 minus 6j, so it's minus 16 minus 12j. Isaac, go ahead. You can still do it with nodal, but it would just be a lot of work. Yeah, definitely. Yeah, you don't want to use, again, time is a factor on these tests, right? So you don't want to, yeah, you could use nodal analysis and solve it all with nodal analysis, but you're going to use a method that's going to take you a long time to solve. And, you know, especially if, you know, some of these, some of the problems, you don't have to necessarily, you can set up a system of equations that you would plug into FreeMat, but some of them are going to ask you to really get the answer, right? And you can't afford sometimes to do nodal analysis if there's a more trivial approach to it. And knowing the op-amp patterns is really, especially when you see a cascaded op-amp problem, it's going to be one of those patterns that we've known before, we've come across before. So you should have those cheap. And you should actually commit them to memory. There's only like a handful of different patterns that you see. There's the summing, there's the inverting, there's the non-inverting, difference amplifier. And for the most part, you're just going to see inverting and non-inverting. Most of those are just, in these quizzes, most of them are just inverting and non-inverting. And if you know what those are, then it's real easy to solve those. Mason? Yeah, the gain of op-amps, of different op-amp patterns. Well, when it comes to op-amps, you mean? Yeah. Is the gain the main thing we want to know when it comes to op-amps? Pretty much, yeah. I mean, that's how they become this this thing that you just idealize, right? Because we talked about how accurate the ideal model is. And, if it's a pattern that you're familiar with and you know the gain, then you can pretty much eliminate the op-amp real easily, right? Basically, what we're saying is once you know the gain of the op-amp, then what you kind of have is, and this is what a more high-level block diagram of a system might look like. You might see something like this, which just has the gain of 1 plus ZF over ZR inside that box, and then here's your V2, and then another thing here with 1 plus ZF over ZR in it with your VO. You simplify that circuit into something that's more abstract and easier to look at. And it makes a lot more sense to follow, see it that way. It's like, we've been doing that from day one. You can sort of abstract away from certain things in mathematics. You don't bother calculating the square root of 2. You can find that number. You kind of memorize the square root of 2 after so many times using it. It's the same kind of thing. It just becomes a symbol that you kind of simplify. What else? Isaac? Am I trying to tell you that there'll be an op-amp on the test? Well, there certainly could be. I don't know if there will be or not, but there will be an op-amp on the final because the final is selected from all these quizzes. Yeah. The final is only quiz questions, and it's multiple choice, and you get no formula sheets at all. It has to all be committed to memory. It's like around 30. No, it's not optional. They're never optional anymore. I'm not gonna make any. You all have to do it. You're supposed to commit them to memory. All those op-amp equations, yeah. Anything, so you should be able to do any of these quiz questions without any assistance before you take the final exam, right? And so you can just practice over and over again and figure out what you need, you know, focus on those areas that you need help on. Isaac? The final review bank is the quiz, all those quizzes, the review quizzes, right? There's the review quizzes, which are just for fun, and then there's the real quizzes that you got points for, but those review quizzes have all the entire question bank that I'm selecting from. Go through the quizzes, yeah. Go through all the review quizzes. Really? Yeah. You know how I love to futz with Canvas. Yeah, I think it's a great final because, you know, if you can do well in that final, you can basically do anything. I mean, those quiz questions are simple, but they're actually deep, and so you know you can't really fake your way through it. You kind of have to know what's going on. And then I get to grade it really fast. That's the main reason. But also, you know, we're always about assessing. We're supposed to be assessing the outcomes and stuff, and it's really hard to assess the outcome of an exam where the grading is kind of subjective when I give partial credit based on, you know, my assessment of what that you seem to have understood, which is sort of, it's really murky when it comes down to comparing people's, you know, learning. So an objective multiple choice test is kind of much more efficient that way. Mason, question? Oh, I just graded by hand. Yeah. About 30. Yeah, you'd be doing it on paper. Yeah, and then I basically just type in all your answers into a spreadsheet and it grades them for me. So, is there gonna be a curve? Square root curve? I don't know. I don't know. I think I might have. I don't know what I did if I took it out last year. Because actually, I think I found last year. I mean, the first time I did it, I had it because it was kind of a surprise. I just threw it at them in the last month. But then last year, the scores were just really good because people had gotten it. That they practiced and they got all those concepts. I mean, I've noticed just, I think the test scores have gotten better because of these quizzes. Because it just keeps you from doing all those dumb things. You've all gotten really good because of them. Yeah. What day is final on? I think it's Wednesday. The final? No, it's just the quizzes. And you just had the last quiz. Yeah. 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 Of course. No, well, I don't know what those chapters are. Assignment 13 and 14, yeah. Whatever those are. The last two assignments, yeah. Yeah. Yep. Oh, I have, before you go, I have one. So basically, yeah. Whatever's on the practice test. Concept inventory, yeah. Yeah, I think we're gonna do that tomorrow, maybe. Yeah, yeah. that's another assessment of the class, which is sort of, it doesn't affect your grade, but actually I think I do offer a little extra credit now on that concept inventory. But it's an incidental, it's conceptual as opposed to numerical, which is harder to teach the concept. People resist. People can even solve things numerically and still not know the concept of what they're doing. Isaac? Yeah, yeah. There's a couple. You can take them next Tuesday if you don't want to take them tomorrow. Yeah, yeah. There's a lab tomorrow. Yeah. Mark? I think it's Wednesday. Sorry? Oh, is there a lab tomorrow? I don't think there is a lab tomorrow. I think it's just it'll just be the end of semester assessments and stuff. So, and it's practicals. What? You mean a lab activity? Well, I wanted to, I didn't get it together, but I wanted to spend more time analyzing that circuit. And maybe I could throw some stuff. That pulse detector, I want to answer the question, and this, I could just throw this out, is how, you know, we're measuring the pulse, when we see that pulse on display, that's because the photocell resistance is changing because of the reflective light from the LED from our skin. And my question is, how many ohms is that photocell changing for us to see that signal? And to know that answer, you have to back out the gain of that amplifier. But that amplifier is tricky because it's not linear anymore, because we're not changing voltage, we're changing resistance. And that gives you a nonlinear equation. And maybe what I could do is just throw up the equation and see, and have people sort of try to linear, but when you have the thing is, when you have a nonlinear equation, it's okay as long as the, when the perturbations are small around a fixed point on a nonlinear equation, it still can be modeled by a linear equation. But you have to figure out what is the slope, between R and V at that point, and then you can figure out what the oscillation in V would be, which is then amplified through that circuit. I think that would be an interesting thing to do, and it might turn into a part 2 of that lab in the future, but I didn't have a chance to kind of put it together. But I think it's an interesting question. Don't you think that's an interesting question? Because I think if you really want to understand that circuit or maybe reproduce it, you really want to have a feel for, what it's actually doing throughout the whole thing. And we can't do that right now because it's nonlinear. And that's why when we had that, and I'd also like to figure out why, because when we stuck that voltage follower after the voltage divider for the photocell, it didn't work anymore. And I think if we look at that original nonlinear circuit and then look at the one with the voltage follower in there, we'll understand why it didn't work. But I want to get some more insight into that. And so that could be our activity. So yeah, our final exam is on May 23rd for this class, which is, that's the Wednesday, right? It's Wednesday. And then and then 12L is post-lab assessment, lab test 3, and lab test 4. Yeah, so these are the lab practicals, and unless I get a chance to modify them between now and then, you were going to, in lab test 3, you are going to measure the step response of a second order RLC circuit. You're just going to measure it. You don't have to derive it. So you're going to build a second order circuit. You're going to hit it with a square wave from the wave generator and use the scope to measure the response. And there's an example of what it's supposed to look like in the handout. And then lab test 4 is you have to measure the phase and the gain of the circuit and the phase difference between the input and output sine waves. So of the same, I think it's the same, or yeah, I think it's a series RLC circuit, but I think it's similar to what. Well, actually, yeah, it might be parallel too. There's a couple different options you might get. So that's a good outcome. Everyone should, by themselves, be able to set up a circuit, hook up a scope and a waveform generator to it, and it's a pretty relatively simple. I think it's a pretty low threshold. It's not a very complicated circuit. A series RLC is pretty easy, but just everyone should be able to do that. I strongly believe. Okay, so if you don't feel you're ready, then you can certainly play around tomorrow and then do it next week, Tuesday. It would be cool, but you don't.
So how is the grading, like circuit and then circuit lab?
Well, they're different classes, so you have a separate grade.
And how come the final project
Because I just said it would. Yeah. But you don't have to apply. I mean, if you want to apply it to your lab class, you could as well. Yeah.
So we have to be here on Tuesday. Is that practical?
If you don't do them tomorrow, you have to be here next Tuesday to do them. Yeah. No, you cannot. Oh, you got something going on? Really, it only takes like half an hour to do this. 15 minutes to do each one. They're really not that stressful. Well, I didn't decide to goof off the whole lab session the whole semester. So, I mean, there are, I will be around. I'll be around on Friday, given the materials final. So if you can't, can't get it together by Tuesday, you could come in. I will be also, I don't think I'm going to be here on Thursday, but I don't think so, but I'll be here on Friday. Yeah, I don't think I have any tests on Thursday. Okay. Awesome. Thank you. I know you'll all do well. It always works out. Always. No, it's a conga line thing playing in my head.
It always works out.
That's going to be your heartbeat. Sorry?